Hello, this is Dr. Trout from the physics program at Stockton University. And today we're going to talk about transmission lines. So previously, when we talked about transmission lines or wires, we considered a wire to be like this perfect conductor with no resistance and no capacitance and no inductance. So in essence, it had an impedance of 0. And now we'd like to look at a more realistic idea. So previously we said that, for instance, if we had a really long cable, right, that it would have we would be able to measure the resistance. And the reason for that is because the resistance of the cable depended on the material it was made out of and the cross-sectional area. So the greater the cross-sectional area, the lower the resistance. And the longer the length, the greater the resistance. Okay. So now let's look at a little more realistic version. So far we've had wires with almost 0 resistance and no reactance. And as the frequencies increase, the wavelets become shorter, right? So each individual, as the frequency increases, there's more waves per second. Therefore, the wavelengths are going to become shorter. And they're going to become incomparable in size to the actual conductor diameter. So if I had an alternate title for this lecture, it would be, what is the electrical impedance of a coaxial cable? And a coaxial cable looks like this. It has a center core, that's a conductor, and then a metal shield, and they are separated by a dielectric insulator, and then they're coated with a plastic jacket. So things like your cable TV use coaxial cables, right? So there's a conductor in the center, and then a braid of usually copper if it's a good quality coaxial cable. And then you use this as, these become your 2 conductors. So I apologize for the quality of this picture, but it's from your book. And what we're doing is we're going to take that coaxial cable and cut it up into little chunks, okay, of length dx. So the inner radius is A and the outer radius is B. So the inner radius of the inner conductor is A, or the core, and the shield has a radius of B. And the length is dx. And let's say there's no resistance. So what we can look at is that this would look like a series of inductors and capacitors. Okay, so here's the inductor and the capacitance of this section, and here's the inductor and the capacitance of this section. So I'll blow it up a little bit. So we take our coaxial cable, we cut it up into little chunks, and it has some inductance. And the impedance of an inductor, if you remember, is omega L, where omega is 2 pi times the actual frequency. And the capacitance has an impedance of 1 over omega C. So as the frequency increases, the impedance due to the inductor becomes larger. And as the frequency increases, the impedance due to the capacitance becomes smaller. And once again, these are lengths of dx. So back in a couple of chapters ago, chapter 2, actually 1 chapter ago, chapter 2, we found that the capacitor was equal to 2 pi epsilon naught times dx over the natural log of b over a. And the inductance equals mu times the length of the inductor over 2 pi, the natural log of b over a. Once again, don't forget, A is the radius of the inner conductor and B is the radius of the sheath. So if we go around these individual loops, right, each loop, here's the first one, we have Vn minus 1 is equal to Vn plus the voltage across the inductor, which back from last chapter was L times the time derivative of the current. So don't forget, if the current is not changing in an inductor, the voltage is 0. Okay. And if it's increasing, the voltage will be positive. And if it's decreasing, the voltage will be negative. And that came from Faraday's law. If we look at the next segment, then Vn is equal to the voltage across the inductor, which is the inductance times the time derivative of the current, plus Vn. If we look at the node where they're joined, we get the current from the first section will equal the current from the second going into the second section over the current that flows through the capacitor. And in chapter 2, we said that the current that flows through the capacitor is equal to the capacitance times the time derivative of the voltage. So if the voltage across the capacitor is increasing, then the current is positive. If the voltage across the capacitor is decreasing, the voltage is negative. And if the voltage is constant, no matter how great it is, the current is 0. So next what I'm going to do is I'm going to take the time derivative of the loop law. So I'm going to take the time derivative of In, which is equal to the time derivative of In plus 1, plus C, the time derivative of V. And what I end up with is the time derivative of the current that's in the nth node is equal to the current going into the n plus 1 node, right? The time derivative of it, plus the capacitance times the time derivative, the second time derivative of the voltage. Because don't forget, it was the time derivative of the voltage. Now we're going to take the time derivative of that. We get the second time derivative of the voltage. So it's d squared V dt squared. Now I'm going to use these 3 equations and plug them into one another. So I have the time derivative of the nth, and I'll solve for the time derivative of n plus 1. And I'll plug it into my equation. All right, so I took the loop law. I took the time derivative of the loop law. I solved for n plus 1, which is the current going into the next segment of the wire. And I'm going to plug it into the loop law. And I end up with this equation down. Okay, so it's the voltage at N here is equal to L times the time derivative of the current in N minus C and the second time derivative of the voltage at N plus V sub N. So I plugged it into this to here, and now I'm going to solve for V sub N, right? I can factor out an L, right? And I end up with this equation down here. So I just copied over that equation, and I'm going to go ahead and multiply through by L, right? So I'm going to clean up this equation a little bit. So this L will cancel, but then I have to multiply this by L, right? And what I end up with is that the voltage at N is equal to the voltage at N minus 1 minus the voltage at N minus LC, the second time derivative of Vn plus 1 plus Vn plus 1. And then I do some math, right? I'm going to solve for Vn, the second time derivative of Vn, right? Which is, this is the voltage at the next segment, the voltage at the last segment, and minus 2 times the voltage at the segment we're interested in. And then I'm going to divide both sides by the length squared. So that's dx squared. Well, on this right-hand side, what this becomes is the second derivative of v with respect to x. Okay. So I'll go ahead and write this as Vn minus, the voltage difference from the next segment to the segment I'm interested in, minus the voltage at the segment I'm interested in, minus the previous one. Okay. And this just becomes 1 over dx times the derivative of the voltage. I do a little more math, and what I end up with is that I'm going to let dx go to 0, in which case the second derivative of v with respect to x is going to be equal to LC over dx squared times the time derivative, the second time derivative of v. This equation should look familiar. And in a second, we'll see why. So what I'm going to do is recall that C and L, C is equal to 2 pi epsilon naught dx and over the natural log of b over a, and L is equal to mu naught dx over 2 pi, the natural log of b over a. I'll multiply both of them together, and I end up with LC equals epsilon naught, mu naught dx squared. So I'm going to plug that in. So LC over dx squared just becomes epsilon naught mu naught. So what I end up with is 1 over epsilon naught mu naught. The partial derivative of v, the second partial derivative of v with respect to x, is equal to the second partial derivative of v with respect to t. Hopefully this should look familiar. Because this is the linear wave equation, right? Which says that v squared, d squared v, the second derivative of v with respect to x, is equal to the second derivative of v with respect to t. That means that v is equal to the square root of 1 over epsilon naught mu naught. Don't forget, this is the permeability and permittivity of free space. And if I plug in the values, I end up with the voltage equal, the velocity equal to 3 times 10 to the 8 meters per second, which is the speed of light. So these waves move through the cable at the speed of light. This isn't surprising because there are electromagnetic waves, and light is electromagnetic wave. So all electromagnetic waves move through a vacuum at the speed of c, 3 times 10 to the 8 meters per second. In a dielectric medium, we should just use the permittivity and permeability of the actual dielectric. Okay, so in this case, what we find is that epsilon is usually greater than epsilon naught, which is for free space or a vacuum, but mu is approximately equal to mu naught. So it's about approximately the same value. But what we find is that the velocity is still 1 over epsilon times mu, but now epsilon is larger, so we see the velocity is slower. So inside the dielectric medium, as these electromagnetic waves pass through it, they're moving slightly slower than the speed of light in a vacuum. Okay, so back to our linear wave equation. We have the velocity squared, the second derivative of v with respect to x, is equal to the second derivative of v with respect to t. And these are partial derivatives, right? Okay, and then what we end up with, sorry, this should be a partial derivative right here. So we end up with the second derivative of v with respect to x is equal to 1 over v squared times the second derivative of v with respect to t. That's how I usually see it written, and that's how I usually like to write it. Once again, v is equal to 1 over epsilon naught mu naught, and if it's in a vacuum, it's equal to 3 times 10 to the 8 meters per second. So if the separation between the interconductor and the shield were a vacuum, then the waves would move at this speed. Instead, it's going to be a dielectric material like plastic, and the waves will move slightly slower. So the solution to this equation, as we talked about the first couple of days of class, will be equal to v naught e to the I plus or minus kx plus or minus omega t, where k is known as the wave number. It's 2 pi over lambda. It's also known as the spatial frequency. That's what we'll talk about it when you take optics. Omega is the angular frequency. It's equal to 2 pi over the period, or 2 pi times the frequency. By the way, the velocity is equal to distance over time. So a convenient distance to use is lambda, the wavelength, and the time for one wavelength to go by is the period, uppercase T. And if we multiply the top by 2 pi and the bottom by 2 pi, we end up with omega over k. By the way, V naught in this case is a little misleading. We usually think of V naught would be the voltage at time 0. But here, it's actually the maximum value. Okay, so if you remember, the current through the capacitor is IC is equal to the capacitance times the time derivative of the voltage, which, by the way, is equal to I at the nth section minus I at the nth plus 1 section, which will be equal to the partial derivative of I with respect to x times dx. So really, this is just the change in I. And we're going to divide by delta x and multiply by delta x. So the solutions to these equations are I equals I naught, the maximum current, e to the I kx minus omega t. And v, we're going to write as v naught, e to the I kx minus omega t plus phi. This phase difference, or this phase shift, is put here to account for the possible difference, phase difference between I and V. So for instance, I might reach its maximum value at a different time than V would. So if we plug this in, we get IC is equal to minus di dx dx. And if we take the derivative of the in dx, it comes out to be ikx, I'm sorry, ik times I sub n. And if we take the time derivative of v, we end up with minus I omega times the voltage at n. Okay, so we took the derivative of I, and we get kx times the function. And then we took the time derivative of v, and we get I omega minus I omega Vn. So C times the time derivative of V is going to be equal to minus di dx dx. And we can plug in for the time derivative of V. We get minus I omega Vn, and plug in for minus di dx, and we get ik in. So let's solve for the voltage, right? The minus signs cancel out, the i's cancel out. We end up with k over omega c in dx. And really, this is just for the nth segment. So we could really just call it Vx is equal to k over omega c I of x dx. So this is the voltage is a function of x, and the current is a function of x. In essence, a function of position. But don't forget, V equals k over omega, we said. Right, so we can plug in for that, and we'll end up with dx over vc is equal to I of x. All right, so we're looking for the impedance. Ohm's law tells us that V equals IR for a resistor. It tells us that V equals IZ, where Z is the impedance, for capacitors and inductors. So for this cable, we know this is what V is. It's equal to dx over Vc, I. So in that case, Z must be equal to dx over Vc, where this is the velocity. So our impedance for the cable is equal to dx over Vc. However, we know that C is 2 pi epsilon naught dx over natural log of B over A. And L is mu naught dx over 2 pi natural log of B over A. And V, we found out a couple slides ago, is equal to 1 over the square root of epsilon naught mu naught. So I'll plug them in. I'll plug in for C. I'll plug in for V. And I end up with the square root of mu naught over epsilon naught, the natural log of B over A, where this is the radius of the sheathing, this is the radius of the inner conductor, and the permeability and the permittivity of free space is epsilon naught, is mu naught and epsilon naught. So unlike, sorry, I spelled unlike wrong. Unlike the resistance, the impedance does not depend on the length. Mu naught and epsilon naught are values for vacuum. So we should use epsilon naught and mu naught for the dielectric material. And we can plug in and find out what we have for Z, which is the impedance. So typical values are 50 to 100 ohms. So for example, your cable TV probably uses either a cable of 50 ohms and or 75 ohms. And it doesn't matter how long the cable is. Okay. Don't forget, we're assuming that there's zero resistance. And for the length of like the cable that runs through your house, it probably is zero resistance. You know, it's probably really close to zero. By the way, there's another method called the twisted pair, where you just take two wires and twist them together. This is used a lot for things like, well, if you still have a telephone that's hooked into the wall that doesn't use your cable line, it probably uses twisted pair at some point. Okay. And what we find is that the impedance is about the same. Okay. All right. So let's take an advanced topic. We're going to send a pulse down our coaxial cable. So here's our voltage, and it's going to reach a maximum and minimum. So we're going to take this Gaussian function, e to the minus alpha x minus vt squared. And we'll send it down the pulse. And let's check if this is a linear wave. Right? So we'll plug it into the second derivative of v with respect to x equals 1 over the second derivative of v with respect to t. Once again, I apologize. This should be a partial derivative right here. If you remember, the reason that this is important, whether it's linear, is because then we can write a Fourier transform for it. And the Fourier transform takes, we'll take our function and we'll multiply it by e to the minus I omega t, right? And we can transform it into a function of frequency instead of time. So we'll go ahead and find out, we'll find out what the transform is. So we're going to change it from variables x and t to variables x and omega. So we'll take our function and multiply it by e to the minus I omega t and integrate from negative infinity to infinity. We're also going to change the variable. So we're going to define something called t prime, and it's equal to t minus x over v. And we'll also remember that omega over v is equal to k. So we'll plug that into our values, right? We get e to the I omega t, okay? And then alpha v squared t prime squared. And we can factor out an e to the minus ikx. And if we do this integral, we end up with e to the ikx pi over alpha v squared to the 1/2 e to the minus omega squared over 4 alpha v squared. So the pulse is a solution to the wave equation. A wire or a coaxial cable is just a special case of a waveguide. So the main limitation we have used in this electric and magnetic fields depend only on X, the position along the length of the cable, and not on Y or Z. This is only valid if the wavelength is greater than the perpendicular dimension of the cable or waveguide. So assume that our maximum fixed frequency is about 50 megahertz, which is pretty fast, pretty high frequency. Right? If we look at the wavelength, it's equal to the speed of light over the frequency. It's about 6 meters. So the wavelength is much longer than the radius of the cable. So we're okay. However, if we look at microwaves and optical waves, so microwaves, their transmission, their waveguides or their wires, if you will, are hollow tubes. So you send the waves down these hollow tubes. And for optical waves, we use either, once again, just air, right? So we could send it through the air, or we use fiber optics, right? Okay. So our wires for optical waves are fiber optics, fiber optic cables. And for microwaves, they're just tubes, right? That are hollow tubes. As these waves travel down, they can have 3 different modes. There can be transverse electric field. That means that just the electric field is perpendicular to the direction of motion. Or transverse magnetic fields, which means that just the magnetic field is perpendicular, but not the electric field. And finally, we have TEM waves, in which the electric field and magnetic field are both perpendicular to the direction of propagation. So there is no component of the electric or magnetic field that points in the direction of or the opposite direction of the travel, the velocity. So traveling waves in a coaxial transmission cable is a TEM wave, right? A transverse electric and magnetic field wave. This is not true for conduits for microwaves, for instance. So let's consider something, a transmission line that we would use for microwaves. Okay, so we have our 2 flat plates, all right, and they have the dimensions d, that's the thickness between the plates, and a width and a length. Okay, and in this case, we have c is going to be equal to epsilon naught w, which is the width, and for the length, we're going to replace it with dx. So if you remember, for a parallel plate capacitor, the capacitance is equal to epsilon naught times the area, the cross-sectional area of the plates, divided by the distance between the plates. The inductance is equal to mu naught d, the distance between the plates, times the width, divided by the width, times the length, and once again, in this case, the length is dx. Don't forget, the velocity will come out to be equal to dx over the square root of LC, just like a coaxial cable, right? So we end up with 1 over the square root of epsilon naught mu naught is equal to c, which is the velocity of light. Okay, so we know that v is equal to 1 over the square root of epsilon naught mu naught, right? And we know that z is equal to dx over vc, which in this case will be equal to the square root of L over C. So in this case, for a flat plate transmission line, Z is equal to the square root of L over C. And we can plug in for L and C, and we end up with the square root of mu naught over epsilon naught D, which is the thickness between the plates, over W, which is the width of the plates. And the power transmitted along this transmission line is P equals delta VI, or since V equals IZ, we can write it as V squared over Z. Don't forget, we always talk about the difference in potential in voltage, right? But since we always do it, a lot of times we leave off the delta and just say V, where it's understood that we're always talking about the change in voltage, not the actual voltage. So we can plug in for Z, and we end up with the power. By the way, we usually don't like to just talk about the power. We talk about the intensity, and the intensity is the power over the cross-sectional area. So we end up with delta V squared over the square root of mu naught over epsilon naught times the distance between the plate over W divided by the area, the cross-sectional area, which is W times the thickness between the plates. And if we clean that all up, we end up with V squared over epsilon naught mu naught. The square root of mu naught over epsilon naught, which equals the square root of epsilon naught over mu naught times E squared. Don't forget that E, the electric field, is equal to the voltage difference divided by the distance between the plates. So we see that the intensity is proportional to the electric field squared. We also have something called the intensity the intensity is actually the magnitude of something called the Poynting vector. And pointing is somebody's name, but it also points in the direction of propagation for electromagnetic waves. And we say that the Poynting vector is equal to 1 over mu naught, the electric field cross the magnetic field. However, don't forget the cross product will be perpendicular to both E and B, which, by the way, is the direction of propagation for the wave. The magnitude of this becomes 1 over 2 mu naught EB, because what we're going to use to solve this equation is, don't forget, we'll use electric fields and magnetic fields that are cosine or sine waves. And if we average over a period, a sine or a cosine wave, we get the value of 1/2, right? So the magnitude of the Poynting vector is equal to, the average value is equal to 1 over 2 pi, 1 over mu naught E times B. So in general, the intensity can actually be written in general, B is equal to E over C. So the magnitude of the magnetic field is equal to E divided by the speed of light. We can also write this as E squared. So S is equal to 1 over mu naught E times B, where E is the electric field and B is the magnetic field. But B is equal to E over C, so we end up with E squared mu naught squared over C. So the magnitude of the Poynting vector is equal to the intensity. If we do a little bit more algebra, we end up with that this intensity, this power per area is equal to E squared over Z in a vacuum, because Z is going to be equal to the square root of mu naught over epsilon naught, which is equal to about 377 ohms. In the medium, right, so this is in a vacuum. If we look in a medium, we're going to use mu naught over epsilon naught, and we're going to define something called the index of refraction. And the index of refraction is the speed of light in a vacuum divided by the speed of light in a medium. So we find that the impedance in a medium is equal to 1 over the index of refraction. And we look up the index of refraction. So for instance, for water, it's about 1.33. And for plastic, it's about 1.5. So the impedance in the medium is 1 over n times the impedance in a vacuum. Where once again, eta, I should say, is equal to the index of refraction, which is equal to the speed of light in a vacuum divided by the speed of light in the medium. All right, so why is this important? Let's say we take two coaxial cables and we stick them together. And one has an impedance Z1 and one has an impedance Z2. What's going to happen is, just like light, when we hit a difference of an index of refraction, what's going to happen is some of the light gets transmitted and some of the light gets reflected. So we're talking about electromagnetic waves again. So what happens is these electromagnetic waves are traveling down the wire. Now they hit this interface where maybe this is a coaxial cable of 50 ohms and this is a coaxial cable of 75 ohms. And what happens is that some of the energy reflects back into the cable and some of it gets transmitted. So another strange thing happens. Note that here the electric field's pointing down and the magnetic field's pointing into the page. The transmitted wave, the electric field is still pointing down and the magnetic field is still pointing into the page. However, the reflected waves, the electric field is still pointing down, but the magnetic field has flipped directions. It's now pointing out of the page. So we have three waves. We have an incident wave. We have a reflected wave, which has the same frequency and wavelength as the incoming wave, but it's moving in the opposite direction. That's why we have that extra minus sign. And we have a transmitted wave. Once again, the same wavelength and the same frequency. The reflected wave will be equal to the incident wave times some factor, R. And the transmitted wave will be equal to the incident wave times some fraction or some constant T. However, the voltage on both sides of this interface have to be the same. So the voltage from the incoming, the incident wave, plus the voltage of the reflected wave have to equal the voltage of the transmitted wave. This means that 1 plus R has to be equal to T. If we recall Maxwell's equation, it said that del cross B, where B is the magnetic field, is equal to epsilon mu, the permittivity and permeability of the medium, times the time derivative of the electric field. However, because of the cross product, E is perpendicular to B. So for instance, here it's pointing into the page and they're pointing down. And the product are both perpendicular to V. So E, B, and the velocity have to be perpendicular. Okay, so we're going to take our wave. Here's E. It only has a Y component. It's equal to epsilon naught. I'm sorry, it's equal to E naught, the maximum value of E, e to the minus kx minus omega t. And B will look kind of the same, only it'll be a magnetic field, and it points only in the Z direction. So if we take del cross B, we end up with IK B naught. And if we take the time derivative of E, we get minus I omega, minus I times minus omega, which is I omega. However, don't forget that omega is equal to Vk, and V is equal to 1 over the square root of epsilon naught mu naught. So what we end up with is that B naught is equal to E over V, and E is equal to the voltage over the distance. So when reflecting, the direction of the magnetic field flips, so the minus sign is added. So in this case, we get the magnetic field minus R times B naught, that's the reflected wave, is equal to T times the magnetic field, the transmitted magnetic field. They have to be continuous across the interface, but their signs are going to flip. But B naught is equal to V naught over VD. And we end up with V naught over the speed times the distance minus R V naught divided by the speed times the distance equals T V naught, right? So we can factor that out. We know that the impedance is proportional to V, which is 1 over epsilon naught, epsilon mu naught. So what we end up with is that we get V over Z1 minus R V over Z1 is equal to T V naught over Z2. So the fact that the voltage must be the same on the interface, we can find out what R is equal to. It's equal to Z2 minus Z1 over Z2 plus Z1. And T will be equal to 1 plus R. Okay, so let's take a couple special cases. Let's short out the coaxial cable. So we're just going to put a wire across it with 0 resistance. In that case, we have whatever Z1 is, but Z2 is going to be 0. So we end up with minus Z1 over plus Z1 is minus 1. And the transmission is going to be 1 minus 1 plus R, which is -1, which is 0. So if we just short out the coaxial cable, what happens is The electric field goes down, hits that short, and then just travels back the other way, unchanged. Right? I mean, the direction changes, but its magnitude is the same. If we have Z2 equals Z1, then the reflected is 0 and the transmitted comes out to be 1. This is good. So if you hook two coaxial cables together, you should match their impedance, right? So for instance, cable companies sometimes have a problem when they're using, say, 75 ohm cables to hook to their devices, but the house was old or something and it was wired with 50 ohm cables. So if the impedance is matched, then there is no reflection and all the energy is transmitted. So if this is a 50 ohm cable and a 50 ohm cable and they're put together, it'll be okay. However, it's a 50 ohm cable and a 100 ohm cable, then we're going to get some reflection. And only some of the energy will be transmitted. By the way, if we make Z2 infinity, so we leave it open, what we end up is the reflection is 1 and the transmission is 2. Okay, don't get worried because it's twice the amplitude, not twice the power. Okay, so the amplitude of the wave is not the power. So what are we talking about here? We take an incident wave and we send it down a line. And for instance, here it's going fast. Here's a thick cable, it's going slow. And we talked about this earlier. We get a reflection and a transmission. By the way, if we're moving from slow to fast, the reflected wave remains in phase with the incident wave. All right, so if you look at the power of the incoming wave, it's V1 squared over Z1. And the outgoing power is V2 squared over Z2. If Z2 is infinity, then P2 is equal to 0. So the amplitude is twice as great, but there's no power transmitted. So in general, we have our power is equal to the voltage over the squared over the impedance, and the power of the reflected is the same. However, we have R squared value there. And for the transmitted, we get T squared. And I'm sorry, this should be a V2 C2. Right, so it's the power and voltage there. Oh, but that would be V1 over Z1. If we plug in the values, we end up with that in general, we'll see that the power reflected plus the power transmitted is equal to the incoming power. So if we take these general cases and we go ahead and plug in R and T, we end up with this. So everything's fine. The reflected power plus the transmitted power is equal to the incident power. By the way, transmission cables do have resistance, so really we should model it like this, right? If the cables are short, the resistance is going to be really close to 0 and you don't have to worry about it. But if we make the cables really long, then we have to add in the resistance. So for our Kirchhoff's loop laws, we have to add in I times R, the resistance of the cable, or that little segment. And we can do the same kind of analysis. Right, and what we'll come up with is that if we use a Gaussian pulse again, we can see that it's still a valid solution. However, what we're going to see is that as, like, if we send a pulse down this cable, it's going to decay as minus gamma t over 2. So as it travels down the cable, if the cable is really, really long, it's the signal is going to decay and get smaller and smaller and smaller. Okay, so this was an introduction to transmission lines and cables.